So our next topic is really quality control and tolerancing. What we did last time was calculate those numbers, kind of look at what they mean as far as the absolute goes. So we calculated LAB, LCH, those kind of things. And now the idea is to look at what exactly do those things mean when we look at quality control and tolerancing. You know, when we talk about quality control in industry, we want to be able to make the decision whether something is acceptable or not fairly easily. If you're making injection molded part and there's a hole in it, important part of that is what the size of it is, what the diameter it is. You can measure that with some kind of measuring device pretty simply. The number means what size it is. Same thing if we're making a bottle and it has to be a certain thickness. You know, you can cut it and measure it, or they even have measuring devices that basically touch up against it, right, and it measures the thickness without having to cut it. But that's a kind of absolute thing. I mean, a measurement of 2 millimeters is 2 millimeters. It's always 2 millimeters. The problem you'll see when we talk about color is when we say a number, it doesn't always mean the same thing visually in all parts of color space. So it's not always the same dimension. So we'll get into that. Much of color technology is concerned with decisions about quality. And when we talk about quality, what we mean as far as color goes is, does this batch of material match the standard? You're a color matcher, you get some part in, say this mouse. Your customer says, I want that color in polypropylene, match it for me. You want to know, does the batch that you made up with your formula match that standard? You want to know, with quality, does this process produce consistent color? So if you make up another batch, does it look the same as the first batch? And so forth. So every time you make it, does it look the same? Whether it's in the lab or in production. You know, that's always important in industry. If not, is that lack of color consistency acceptable? Any industrial process has some variability in it. Is that variability too much? No matter what you do, it's going to be out of spec because you just don't have enough control over your process? Or is the variability okay and you can still make your good parts? And that's true of any plastic process. You know, in blow molding, injection molding, there's some variability. The question is it acceptable? Because you can't get rid of all the variability. Lastly here, can this new part be used interchangeably with parts made last month or last year? If your customer buys parts from you or buys color from you this year, new order next year, do parts from the same batch match? Think of Stylecrest, they make siding. If you put your siding up this year and then next year there's a big storm, blows part of it off, you go buy some more of the same color, put it back on your house, doesn't match. You know, that's important. Ideally, the answer should be yes. Practically, the answer isn't always yes. So all of the preceding questions relate to color quality. The first step in measuring color quality is recognizing that there are two types of visual assessments: perceptibility and acceptability. So what we mean by perceptibility is you can actually see a color difference. Can I see a difference in the color? Yes or no? Is this color difference greater than or less than the difference in the color between members of a standard pair? You can see a color difference. Just because you can detect it with your eyes, that doesn't necessarily mean that it's not an acceptable match. You know, there's a range of closeness that's acceptable. Because if you have to be absolutely perfect match with no perceivable difference, you make it pretty tough. That's where acceptability is important. Is that difference between the standard and your batch close enough to make it acceptable? Or is it so far off that the customer won't accept it? So that's important when you are trying to make your decision. Some customers would like to use perceptibility and they want it to be perfect all the time. But, you know, that's pretty difficult to do and sometimes impossible to do in some circumstances. problem with using perceptibility measurements for quality judgment in industrial process is that the natural inherent variability of the process is too large. If you make a batch and then make another batch and make another batch, you're going to get differences. I mean, it just can't be exactly the same all the time. Think of your blow molded or injector molded parts. If you were to measure every one of them, you know, there would be some variation in them. Even if everything was running as good as you could get it running, there's inherent variability in the process. If you work with quality control, and especially statistical quality control, you measure variability. That's very important. The question is that variability small enough where you can still have that variability and not go outside of your required tolerances? So tolerances are how big of a range is acceptable. The variability of your process needs to be within that range of tolerances. If it isn't, what we say in quality control is that you don't have the capability of making that part under those conditions. In industrial process, we use the acceptability criteria for making quality judgments. So somewhere along the line between yourself and your customer, you need to somehow determine what makes the product acceptable, whether it's color or anything else. In color, we need to determine how close the match must be determined by an agreement between the customer and the supplier. So important factors include the application. For instance, if you're doing automobile interiors, you're probably going to have smaller tolerances than if you're doing cheap snow shovels or cheap toys. Cost is an important thing. Maybe the guy that's making the cheap snow shovel wants the same tolerances as our automobile manufacturer, but he's not willing to spend more than $1 a pound for the colorant. Well, that's not going to work. I mean, cost is certainly a consideration there. The closer you want the tolerances, most likely the more it's going to cost you. And also what the consumer requires. Kind of comes down to that. If the consumer requires very tight tolerances, then that's what you have to meet. If they don't, then you can have a little bit more relaxed tolerances. For the purpose of this discussion, we will deal with color quality control based on color instrumentation. So we're going to look at this whole quality issue in terms of numbers. We will assume that the experienced color matcher makes the correct pass-fail color decision. Our absolute right-wrong answer is based on what an experienced color matcher sees with his eyes. You know, we always say that it comes down to, does the color look good? And really it kind of goes back to not just the color matcher, but the customer. The customer says it's no good, no matter what you tell him. If he doesn't like it, then he's right. You know, if he doesn't accept it, then it doesn't matter if you think it's right on, it's no good. But that's what we're going to use as our correct decision, let's say, what somebody sees with their eyes. So what we're comparing to that is how well does the instrumentation calculate the numbers, agree with that. So if we say, yes, that's acceptable match, do the numbers say, yep, that's an acceptable match? And if we say it isn't, do the numbers say the same thing? And that's really what's important when we look at this. The history of instrumental quality control can be summed up as the relentless pursuit of perfect correlation between visual color perception and numerical color differences. We want to correlate those two things. We always say visual is what we want to model, so we want to know how good do our color difference equations come to that. When two samples visually match, the goal is to have the corresponding calculated difference values be within an agreed upon tolerance. So if we say our tolerance is 1, total color difference of delta 1, so if it's above 1, it's unacceptable, and if it's below 1, it's acceptable. When we look at a pair of samples visually, we want to make that pass-fail decision, and then we need to use that number of 1 to agree with that. So every time we visually say two sets of colors match, the difference number should be less than 1. And if every time we say they don't match, when you get the color difference numbers, it should be greater than 1. That's what we're talking about here. This 100% correlation is desirable to allow for color acceptability judgments to be made exclusively on objective color measurements and less subjective human assessment. That's kind of the goal, is to use numbers to make the decisions instead of people to do it, where their judgments are sometimes flawed. Not every person making the color judgment has the same color vision, the same aptitude, the same motivation. By taking the person out of it, kind of, and using numbers, we take that variability out of it. For a manufacturer of manufactured goods, this means the same decision is made on first, second, and third shifts, no matter who's making the decision and what mood they're in or how long they've been up and whether they had to fight with their wife before they came in, whether they're mad at their boss, or the quality control person has a fight with a machine operator, so no matter what they turn in, they're going to say that it doesn't match and, you know, that kind of stuff. Instruments don't care about any of that stuff. Our basic model for measuring color, we already described. You got to have your illuminant, object, and observer, and you get our tri-stimulus values. We've talked about those, capital X, Y, and Z, tri-stimulus values. So they are used to identify the color of an object or light source using 3 numbers. And then we change them into our more familiar in industry LAB numbers, LCH numbers. We'll see there's something called CMC. There's many numbers that are used in our quality control procedures, quality control operations. Talking about tri-stimulus values again, the values of the CIE 1931 system can be used to specify color very precisely, but unfortunately direct correlation with visual judgment is difficult. About the only one we use is Y, capital Y, for lightness. X and Y don't correlate very well with anything else. We have to convert these tri-stimulus values into other numbers to make them more meaningful. Transformation. So we need to take those tri-stimulus values, our capital X, Y, and Z, and put them into other forms. Researchers over the years have applied nonlinear transformations to tri-stimulus values with the goal of creating uniform color spaces. So that's one of the things that the mathematicians, mainly mathematicians, were working on, is to take our color space, which is inherently nonlinear, which means the numbers don't mean the same thing in all parts of color space visually as they do just with the numbers, and somehow transform them so that we have a uniform color space. These uniform color spaces would then allow calculation of meaningful values for color difference, magnitude, and direction. The problem is, think of if we were going to drive from here to California, let's say, and we wanted to determine how many miles it was to drive there. The way we are now, it would be pretty easy. We could measure how many miles it took, because everywhere we would go, a mile equals 5,280 feet, right? Well, what if every state had different requirements or different definition of what a mile was? What if in Ohio it was 5,280, Illinois it was 4,000, Nevada was 6,000, get to California, they're really screwed up, 20 feet. Then when you got there, how would you know how many miles you went? Well, it'd be pretty hard because you couldn't compare the numbers easily because they mean different things in different places. That's what the problem with these color spaces are. The distance apart for 2 samples visually means in one part of color space would be a certain distance, and in another part would be a different distance numerically. So they wouldn't correlate. So it's hard to compare that. So we'll look at several equations along with their corresponding color space and determine their acceptability for using to develop industrial color tolerance values. We'll look at chromaticity coordinates, CLAB, LA and B, CLAB, LCH, all of those we've talked about before, and then we'll look at something new that's called CMC. The first attempt was to use chromaticity coordinates to develop a diagram and a color space. So the CIE proposed using These values, they use X and Y as the color coordinates basically, and capital Y would be our lightness value. We have our equations here for the chromaticity coordinates that we've gone through before. X plus Y plus Z equals 1, and then the individual small letters X, Y, and Z for the chromaticity coordinates are the proportion of each one of those in the total. This should be Y and Z there instead of X. Through that. Chromaticity coordinates represent the proportion of the individual tristimulus value out of the total of the three values. We can look at a visual and graphical representation of the chromaticity diagram. Chromaticity coordinates of the pure colors of the visible spectrum form the shape of a horseshoe known as the spectrum locus. So that graph or plot we showed before looks like that, where we have along the outside of it numbers that represent the individual wavelengths of pure color. In the center we have where the light sources are, and then the farther out you get to the center, the more chromatic it gets. The direction gives you the hue. And we did some calculations before. The farther you get to the edge, the more pure the color is. We use the number called purity, and then if we draw a line from the light source through the sample and then intersect the line with the wavelength numbers on it, that gives us our dominant wavelength. So those are kind of what the numbers mean. There are some problems, though, with using this diagram for tolerance. The physical distance between two samples, not consistent throughout the diagram. Diagram not uniform with visual perception standpoint. So there was a famous color scientist named David McAdam that studied this diagram very closely, and he documented the problems that were inherent in this system. It's based on using colored lights. What he did is he had a standard color, the color he was working with, and then he changed the lights to produce just a perceivable difference. So the idea was how far off the values for the lights would be before the person could detect that there was a difference. Did a lot of different colors in different parts of color space. Found that the data resulted in ellipses of various sizes, which means, ellipses here, the center point is the target value and the outer line represents the farthest acceptable match. Colors within the ellipse are acceptable match to the target, values outside are not. This is what that looked like when he looked at the data. And what this shows is that we pick one of these ellipses, we see that this is our target. Anything that falls within there, within this ellipse, that outer line, would be perceived as the same color. And what he noticed when he looked at his data is that when we were up here and in the green area, the numbers could be very far off, especially in this direction, going up and down. Person would say, yep, those still match. I don't see any difference. Down at the bottom end, in the bottom left here, we could have, a number, say this value here, distance-wise, down here, that we would have the same calculated number, but now it would fall way out here. And if it fell out here, what would that mean as far as visual color perception? Would it match or not match? Wouldn't match, right? And that's a problem. It's kind of like my example before. Miles here are different than miles here. It's hard to compare those two. And if you notice, it's not uniform in all directions. If that were the case, we'd have our center point and the outer line would be a circle. But it's not. It's an ellipse. So even in a certain part of color space, if we said, let's take this distance that's about that far, so in this direction, it would be outside of it, so that number would be unacceptable match. But if it was this direction, that very same value would fall within this ellipse, it would be acceptable. Depending on which direction it's off, that also affects how we perceive the color. Hopefully, with this explanation, you get the idea that it's not very good to use these numbers for color tolerancing because they don't mean the same thing all the time. If you're in one part of color space, a certain number of, say we use delta 1 of 1, might mean that it's acceptable. But in another part of the color space, it wouldn't be acceptable at all. And even which direction it was off, that could be the case. That doesn't lead to too much consistency in using that. Notice that the ellipses used for determining acceptable matches vary greatly in size, different parts of the diagram. And what that means to us practically is that a certain value for a difference in one area of the diagram will not be the same in a different part of the diagram. So depending on what color we are, we'd have to use widely different numbers for our tolerances. It'd be like if you were making bolts and you were measuring a bolt. If you made it on this machine, you would use 3 inches as your tolerance, plus or minus, say, 10 thousandths. And in another part of color, or another machine in a different part of your plant, you would use 3 inches plus or minus a half inch. Wouldn't make a whole lot of sense. Unfortunately, the chromaticity diagram is very nonlinear when compared to visual observations. That's kind of a mathematical way of describing it. The same numerical values in various parts of the color space represent vastly different visual color differences. For instance, a numerical difference in the green area of a diagram of 1 could match, but a 1 in the red area probably wouldn't match, even though we're using the exact same numbers. Because of this large variability, or nonlinearity, of the color space described by the chromaticity diagram, it is not used for color tolerance. So we've kind of moved on from that.